This lesson is going to be covering curved mirrors. We'll be looking at a very specific type of curved mirror called a converging mirror. So you should have out with you your note template ready so you can follow along as we go through this. So this is something that we've talked about when we looked at plane mirrors. This is how we describe the properties of an image that's formed from a mirror. I won't spend too much time here because we've already talked about it. So we can talk about the size of an image. Is it larger, smaller, or the same size? The attitude or the orientation. Is it right side up, upside down, or inverted? The location, which means how far is the image from the mirror. Is it in front of the mirror, or is it behind the mirror? We can have the type of image, which means is it virtual or is it real? So again, a virtual image is when the image is formed behind the mirror, and the real image is when the actual incident rays come together at a point and form an image that's in front of the mirror. And we had a chance to see this with the demonstration we did last class. So when we're talking about a curved mirror, there's some certain features that we have to consider. So if we think about this here as being our curved mirror, I can extend that curved mirror around till it completes a full circle. And I want to think about that as being sort of an imaginary circle, and the center of that circle is a point that we call the center of curvature. And all mirrors have this center. It might be in a slightly different place depending on how curved the mirror is, but it's going to be the center of the circle that's formed if we extend the mirror all the way around. And of course, the distance from the center of a circle to the edge is called the radius, and we refer to this as the radius of curvature. But more specifically, rather than calling this the radius of curvature, we normally just refer to it as something called the principal axis. So you're always going to see this center line here that comes through the center of your mirror, and we refer to that as the principal axis. The point where the principal axis meets the mirror is called the vertex, and sometimes in your diagrams you'll see this point labeled with a V, or occasionally they'll use the letter A. So this is the vertex. This line represents the principal axis, and this dot here represents the center of curvature. So those are just some terms to be familiar with as we go through curved mirrors. Now, curved mirrors can either have the mirrored part on the inside here, on the inside edge, or the curved mirror can have a mirrored surface on the outside. And those are the different types of mirrors that we're going to be talking about. So the first one is called a concave mirror. So you can see here that the shiny part or reflective part of the mirror is on the inside, and as light hits this mirror, it bounces the light back. So in the dead center of the radius of curvature is a point called the focal point, and we call that point F. And the focal point is shown here, and that's the point where all of the rays that travel parallel to the principal axis reflect through. So any time we have a ray that's parallel to the principal axis, it will hit the mirror and reflect directly through F, which we call the focal point. Now, depending on the type of mirror that we have, this focal point can be either in front of the mirror or it can be behind the mirror. And this makes sense because if we think about this convex mirror or diverging mirror, the mirrored surface is on the outside, but if we extend this full circle all the way around, the radius of curvature would still be here on the inside, and therefore the focal point is actually behind the mirror. And the reason this is called diverging is because the light rays hit it and bounce away, whereas with this type of mirror, the rays hit the mirror and bounce inwards towards this one focal point. So we have a concave or a converging mirror, and a convex or a diverging mirror. So what we're going to move into now is how to actually draw a ray diagram to locate the image that is visible in a curved mirror. And some few tips for success that we take with us from when we talked about plane mirrors. You should always be using a ruler. So if you don't have your ruler out, you want to get that ready now. Always use arrowheads to indicate which direction the light is traveling. And when we have an object, remember that the light reflects off the object, hits the mirror, and then travels to the eye. Rays that are in front of the mirror are drawn as solid lines, and those that extend behind the mirror are drawn as dotted lines. Something that's going to be a little bit different this time is that when we draw the ray diagram in a converging mirror, we're not really going to worry about where the observer would be. And the reason is that the image is going to be the same image no matter where the viewer is located. So when we're drawing our ray diagrams for converging mirrors, we must draw two incident rays starting from the top of the object in order to locate where the image is. After reflecting off the mirror, the point where these two rays cross is where the image will form. So what we want to figure out is if two incident rays come off the top of our object, reflect off the mirror, where are they going to cross? And once we know where they cross, we know where the image will be formed. Now this rule changes actually depending on the type of object we're looking at, but in general it's sufficient to draw two rays to locate our image. There are cases where we'll have to draw more than two rays, and I'll touch on that a little bit later. So before we start here, you're going to actually have to draw in your object. So I'm just going to draw an arrow, and that's going to be our object. So our arrow will be positioned like this, directly on the principal axis. Now you can draw this in on your page. I give you a little template to start with. So step one is to draw a ray that goes from the top of the object and is parallel to the principal axis, and then reflects back through the focal point. So you'll just have to grab your ruler and go ahead and do that. So again, once the parallel ray hits the mirror, it's going to reflect back directly through F. The next ray is going to come from the top of my object. It's going to flow or pass directly through F and then reflect back parallel. So it's the opposite of the first ray. Notice that I also put arrows on my rays to show the direction that the light is traveling. The light reflects off the object and hits the mirror. So there's my first ray that goes directly through F and hits the mirror, and then it's going to reflect back parallel. It's important here to locate the point where these two lines intersect, because that's the point where my image is going to form. So that point right there represents the top of my object, or in this case the top of my arrow. And since the arrow sits directly on the principal axis, I can just sketch in the rest of the arrow, and that is my completed image. So all it takes really are just two rays. So if we take a moment here to describe the properties of our image, you'll see that it is smaller than the original object that we started with. It is inverted or upside down, and the image is located between C and F. And this is a real image since it's formed in front of the mirror and not behind the mirror. So some other things to keep in mind is that a ray that's aimed directly at the vertex will follow the law of reflection since the principal axis is perpendicular to the mirror. What that means is that if I fire a ray directly at the principal or directly at the vertex, it's going to reflect back at the same angle or at an angle that's equal to the angle of incidence. That's only if a ray is shot or aimed directly at the vertex. A ray that passes through F is always going to reflect parallel to the principal axis. Now we saw that rule applied during our ray diagram, but these are just two rules to keep in mind. So what I would like you to do now is take a break and move on to the practice. Once you feel like you've mastered the first few ray diagrams, come back to this video and watch the remaining bit on some special cases related to converging mirrors. So earlier I mentioned that when we're drawing the ray diagram for an object that sits directly on the principal axis, we only need to draw two rays. So this arrow or this object sits directly on the principal axis. So I can draw my first ray, which goes parallel and reflects through F, my second ray, which goes directly through F and reflects parallel, and this point right here is going to correspond to the top of my arrow, since that's the point where the rays started from. Now, since the bottom of the arrow sits directly on the principal axis, I'm able just to use the principal axis here as the bottom of the arrow, and I can put my image in directly like this. So here's my image. So this changes when my object is not directly on the principal axis. So notice here's my arrow, which is my object. It is sitting off the principal axis. There's a bit of a space here. So my first ray and my second ray are not enough because this point right here represents the top of the arrow, but I have no idea where the bottom of the arrow would be. It would not be correct to draw the bottom of the arrow here along the principal axis and fit the image in this space. Since there's a space here, there has to be a space between the principal axes and my image. But the question is where, and how big should that space be? Should my arrow be pointing this way, or will it be pointing in a different direction? Maybe it's coming from down here. So what I'm going to do is draw another set of rays from the bottom of my arrow. So there's my first ray, which goes parallel and then through F. My second ray, which goes through F and then parallel. Now I have a second point here, which represents the bottom of my arrow. So if this is the bottom of the arrow, this is the top of the arrow, I can put the image in, and I've correctly drawn a ray diagram for this object. So this only matters when the object is not directly on the principal axis. That's when we need to draw 2 sets of rays, or 4 rays in total, in order to properly locate the image. So 2 special cases I want to cover. We're going to be experimenting with our images, or sorry, our objects at different locations. There's 2 special cases I want to go over. When your object is directly at the focal point, and you can experiment and try this on your own with some of the practice problems I gave you. When you draw the rays, you'll find that the rays that reflect back are parallel to each other, which means they never cross. And since they never cross, it's not possible for an image to form. And so if we have an object that's directly at the focal point, we will not see an image of that object, since the rays are parallel. Second special case is when our object is between the focal point and the vertex, or the focal point and the mirror. So when we have our image there, if you trace the rays, you'll notice that our reflected rays here are diverging. They're moving apart from each other. So if we keep extending these rays this way and out this way, they're never going to meet. So instead I extend them back and I form a virtual image. And this is the only time we see a virtual image with a diverging mirror, or sorry, with a converging mirror, and that is when the object is between F and the mirror. That's it for converging mirrors. Again, what it comes down to is just practice the problems and get a sense of how the different rays interact with one another.